So we have water. It's an ideal Rankine cycle, so let's just list out some of the stuff we know here. We have a condenser pressure. It's saturated vapor entering the turbine. It gives the pressure there. We want to get the heat transfer per kilogram at the boiler and the condenser. And then we want to calculate the efficiency. So always with these, let me draw the temperature entropy diagram. This is just an ideal one. So here's our state 1, our state 2, 3, 4. Okay. And from 1 to 2, let's just regain our bearings on this stuff. So yeah, what's the process from 1 to 2?
Isentropic turbine.
Yep, perfect. Remember all the vertical things have to be isentropic. And then 2 to 3.
Isobarbaric.
That sounds horrible.
Yeah. Condenser.
Yes. And then 3 to 4.
Isentropic pump.
Perfect.
This is the boiler.
Boiler.
Yep, perfect. Okay, and our goal always on these is just to come up with the enthalpies at the different states, at those 4 different states. And the stuff we know is
It's an intense sharp finger.
Oh, it's a pencil sharpener.
Yeah. We know that I think this is always good stuff to keep sort of on hand as you do this. We know that the rate of work at the turbine per mass is H1 minus H2. At the condenser, QC dot over M dot is H2 minus H3. At the pump, remember this is where we have 2 ways to represent the rate of work per mass. We can use enthalpy, so it's H4 minus H3. Or we can use the fact that this is an incompressible material through the whole process and represent this as the specific volume times the quantity pressure 4 minus pressure 3. Okay, so that's the one place where there's kind of multiple ways to represent this. And then the one that I don't have yet is the boiler. And so this is going from 4 to 1, and so we would write this as H1 minus H4. Is that right? Yeah, that's H1 minus, I'm trying to think of the first law for control volumes in my head.
It is.
That is right, okay.
QB over M dot.
Okay, so remember these all come from the control volumes first law. And so the order that you're subtracting, remember, comes from the fact that you have the M dot times H inlet minus m dot times h exit. Okay? And each one of these inlet is the starting state. And
So yeah, if you think about the sign in
Yeah.
front of Q and W.
so if you think about the sign in front of the Q and or W, that'll tell you which order those have to be subtracted in. Yeah. Okay, so this tells us this is everything that we're trying to calculate. The one place where you have multiple ways to calculate energy per mass is when we have the incompressible material. It just depends on what information you're given. And so now let's start filling out kind of like a list of what we know at the different places. So state one. Let me just write this all out. So state one to state two to state three to state four. And 1 to 2 is the isentropic turbine. 2 to 3 is the isobaric condenser. 3 to 4 is the isentropic pump. And then 4 back to 1 is the isobaric boiler. We're told that the condenser, now the condenser is isobaric, so it just gives you one pressure for the whole condenser, is 6 kilopascals. So P2 is 6 times 10 to the third, and that means that P3 is also 6 times 10 to the third. And at state 3, let me say what we know about the states here. So at state 3, we know this is a saturated vapor. I was just saying that I assigned problems 1 and 2. I don't know if you've started working on number 2 yet, but okay, so far so good. I assigned that too early. We haven't talked about that yet. So,
Or is it number 1 though? Oh.
Yeah, so we're doing number 1.
Number 1 right now.
Yeah. Okay, so it's a saturated vapor, which means this pressure now is enough for us to look up anything we want. Okay.
Isn't it a saturated vapor? There's the turbine, not the condenser.
Saturated, I said that, yes, I should not have written vapor. I should have written liquid. The reasoning's the same, but yeah, it's a liquid. Right, thank you. The turbine, just what it said about the turbine reminded me that to write this stuff down. So going into the turbine, we know that it's a saturated vapor. And we're given a pressure of 10 megapascals. So P1 is 10 times 10 to the 6. And since that's also saturated, we know that this is enough to look stuff up in a table. What else does it give us? That is all it gives us. We do know that since the boiler is isobaric, we know that in the boiler, the pressure has to be the same as it is at state 1. So P4 is equal to 10 times 10 to the 6 pascals. But state 4 is a compressed liquid. State 2 is a saturated mixture. So neither of those we can't look stuff up yet for those. Okay, and this is kind of like our starting point. So now from the table for state 1, we can look up enthalpy, which is the thing we want eventually, and we can look up entropy. So H1 is equal to 2724.7 times 10 to the third. And S1 is equal to 5.614 times 10 to the third. Okay, so of course we know why we need to look up the enthalpy. But why do we want to look up the specific entropy here? What's the benefit of that?
Because of the isentropic process.
Yeah, exactly. Since this is isentropic, here we know that S2 is also equal to, 5.614 times 10 to the third. And since this is a saturated mixture, we can use this entropy and look up the liquid and vapor values in the table to find the quality. Okay. Once we find the quality, then we can calculate the enthalpy. Are you with me on that? Okay. Same thing with state 3. We can look this stuff up right away. So at a pressure of 6 times 10 to the third, the specific enthalpy is 151 times 10 to the third, and the specific entropy is 0.521 times 10 to the third. And because it's isentropic going from state 3 to state 4, we also know that entropy at state 4 is 0.521 times 10 to the third. Okay, so now we're going to start working with state 2, figure out the quality, and use that to calculate the entropy. So this is a saturated mix, which means that we need the quality. And so we can say 5.614 times 10 to the third is equal to X times the value we look up for the saturated vapor of the specific entropy. That's 8.33 times 10 to the third. So this is S sub G plus 1 minus X times the value we look up for a saturated liquid, 0.51 times 10 to the 3. So that's our S sub L. And now we can go, there's only one variable, we can calculate that quality is equal to 0.653. So by mass, it's 65.3% vapor. And now we can say that the specific enthalpy at state 2 is equal to 0.653 times the value we look up for a saturated vapor, 2567 times 10 to the third. This is our H sub G, plus 0.347 times 151 times 10 to the third. This is our HL, and we get an H2 of 1728 times 10 to the third. Okay, so now we know H2. We know H3. The last thing we have to figure out is H4. And there are two ways to do that, depending on whether we... So now we'll go to state 4. You know, this is the last state. Where we don't know the specific enthalpy. There's two ways to calculate this. We could do a kind of reverse lookup based on, you know, we do have two properties now, and any two properties mean that you can look up anything else, but that doesn't mean that it's that convenient to do. You could, well, we were just talking about AI. Well, this is kind of like the easier version of the reverse lookup, you know, so like,
How the hell did it catch your eye?
well, I typed it in. Yeah. What? Yeah. What's the specific enthalpy at a pressure of 10 megapascals kilojoules per kilogram Kelvin.
For water.
Yes.
Have you checked this?
No. I mean, I have an answer, so we'll see how close the... Okay, 140.8. I got a pretty different answer, but how did I... Well, so, I mean, that's one thing that you have available, you know. That makes all the, you know, the stuff about interpolation and stuff unnecessary. So 140.8. Let's calculate it the other way. Let's assume it's incompressible and see what we get. 140.8 times 10 to the third.
Yeah.
Same fault.
Yeah.
Been lied to before.
I know, exactly. Yeah. AI says H4 is 140.8 times 10 to the third. Okay. Well, we are going to use
Well, it makes sense that it wouldn't change that much, right? Oh, through the pump.
the entropy,
The enthalpy.
the enthalpy. Well,
Is that the value you just got? That, or you got the entropy? What?
oh, you're.
I'm sorry. What was that value?
That was enthalpy, I hope.
Yeah.
Yeah.
And so I was just saying that because the
Mhm.
enthalpy 3 was 151.
Mm-hmm.
So super
Okay.
close, and it
Yeah.
it shouldn't change that much
Right.
through the pump, right?
Yeah. So okay, so let's make the assumption that it's incompressible. So we have H4 is equal to H3 plus the specific volume during the process times the pressure 4 minus the pressure 3. I think that's what it said. Yes. So H4 is equal to our H3 was 151. Our specific volume for water. Now, we could look that up for the temperature range. We haven't thought about temperature yet. I'm just going to assume that this is 0.001. But let's see, what could we do if we wanted more accurate here? Well, we know it's a saturated liquid at state 3. So you could look up the specific volume at this for a saturated liquid at this pressure, and it would give you something a little more, with a little more precision. But that always works pretty well. And then multiply by P4 minus P3, so 10 megapascals minus 6 kilopascals.
Well, it's definitely going to be different. It's going to get bigger. $994.
So I got 161 basically, times 10 to the third. Yeah. So I don't know, those answers are different by
Is that a lot?
15%.
Which one's more better?
It does seem weird that it P4 minus P3. Well, I mean, if the AI stuff comes from, I assume that comes from like function calculations, the ones that they use to make the tables. So so I think
I feel like it just like took the value, took some value off of a table.
mhm.
It explained its process. I don't know. So it went in the steam table. It found the row
Mhm.
corresponding to that.
Right. So if they did that right, I mean, that's more the stuff coming from tables, coming from the functions is always more accurate than making assumptions. But usually those incompressible assumptions are pretty good. So I'm surprised that it's that different.
I bet you it didn't interpolate.
I mean, I think it just had, that could be, but
bet
I think
you-
it's
bet
probably
you
just,
like
yeah,
rounded and
maybe.
found the closest row.
Yeah, maybe you're right.
I don't know.
Okay.
Oh well.
We'll never know.
Okay, so that's H4. So now we have all the enthalpies.
But now AI will say, oh, this answer. Maybe correct itself.
Yeah, you're right.
Well, like, how different are those two really?
Yeah.
Like,
I mean-
I guess I'm asking. Like,
No, I know. Let's try them both, and
Well, something
I'm
else.
sure we'll see that the efficiency basically isn't changed in the least by it. You know.
I'm curious. It's especially with thermodynamics. It's like so easy to like not really be able to understand what numbers you're really working with.
Yeah.
Like, what's 20 enthalpies?
Right. Right. Okay, so what do we want to calculate? Now we want to calculate, obviously, the efficiency. And the efficiency is, anybody have that in front of you?
1 minus H2 minus H3 over H1 minus H4.
H1 minus H4 on the bottom?
Yes. 2 and 3 on the top, 1 and 4.
Okay, so using the incompressible assumption, this is 1 minus 1728. I'm going to leave off the times 10 to the thirds. Those all just cancel. Minus our H3, 151. Divided by H1, 2725. Minus 161.
That's not much of a difference at all.
Mm-hmm. So I got 0.385. Compared to 1 minus, so 1728 minus 151 divided by 2725 minus 141.
Like 387.
0.38. Yeah, so I rounded about the same as I did here, and I got 0.390. And then we want to calculate the heat transfer rates. And I guess let's calculate the rate of work per mass flow rate too. So at the boiler, this is H1 minus H4. So that is 2724.7 minus our H4. I'm going to just keep using the incompressible one. 161. So this is 2563.7 times 10 to the third. And this is in joules per kilogram. Then at the condenser, H2 minus H3. So 1728 minus 151. So this is 1577 times 10 to the third joules per kilogram. And then the rate of work that's being done by the turbine. So this is the power output of the thing. H1 minus H2. They need to oil that thing.
Intense writing.
27, 24.7. So 24.
Or maybe sharpen it.
I wonder if it's one of those crappy ones where it just keeps eating the one side of the pencil.
Yeah.
Oh, sure.
Do you think there's still companies that make wall-mounted?
Definitely.
Do you think it's like $1 billion industry?
Definitely not.
At the corner market, they can charge whatever they want for it.
That's true. Okay, 27, 24.7. And then minus 1728 point. So this is basically 1.00 times 10 to the third. No, times 10 to the sixth. That would be weird. 1,000 times 10 to the third joules per kilogram. And then, I mean, what are the other possible things they could ask? What about the work that's input at the pump?
So if you were to use that specific volume one, would you just like try and pick a representative specific volume between the two? Or wait, no, it's at that state, right?
For which?
Well, you mentioned there's the two ways to calculate the work at the pump. There's
Yeah.
The difference in.
Oh, yeah, right. So yes, you would use the same, I mean, we already made this assumption before. You can always call that 0.001, or you can use the saturation tables at one state or the other to know that you're in the right temperature ballpark.
Sure.
But anytime you look up the specific volume for an incompressible thing, you can use saturation tables, whether it's saturation or not, because you're just trying to look for the right temperature range.
Okay.
You know, so it'll get you a little closer, you know.
Got it.
So H4 minus H3. So we got 161 minus Oh, this is really interesting, actually.
Oh, the pump is generating power.
Yeah, exactly. So, so with our assumption, we got that the pump requires this much energy to power it, and that makes good sense.
Does it? If work is
This,
positive?
yes, because we call, so this is making the incompressible assumption. So we call WP positive when energy is coming in.
Oh.
And so what this says is that answer we got from AI is the one that doesn't make any sense. That AI result says that the pump is producing power.
Mhm.
So, huh,
I have a strong suspicion that it didn't
Interpolate.
do any interpolation.
Yeah. It still seems surprising to me because how much could things be changing at that, but
It's good.
it's very weird.
It's good reinforcement to not.
Yeah, seriously.
Very interesting. So, that seems. Yeah, so that's positive if our. It's like opposite.
Right. Just like the heat going out in the exhaust, we know that that's leaving the system, but it's positive because we're making all the sign assumptions of what we know is really going to happen in the cycle. So notice the result AI gave us says the pump outputs power. And clearly that's impossible. So this is the result from using the incompressible assumption.
Very interesting.
That is interesting. And so now you can calculate stuff like the back work rate and the total, the net power generated. Any other questions about that one? Okay. Well, the next thing we're going to talk about is superheat. Let's do that next time. Let's just stop there.